Hi everyone, today's topic is linear regression, one of the most basic, nevertheless powerful, techniques in machine learning. In order to fully understand this brief lecture, you should know the basics of linear algebra and the differences between overfitting and underfitting. If you have no idea what I'm talking about, I'll leave some resources in the description of this video. Let's start. Regression is one of the main problems tackled by machine learning. We define regression analysis as a set of statistical processes for estimating the relationship between a dependent variable, which we often call the target variable, and one or more independent variables, which we call features. In linear regression, we aim to find the best hyperplane that is able to predict the target variable starting from a set of features. One trivial example could be estimating the price of a house starting from the house's dimension, expressed in square meters. In this case, since we're just considering one feature, the dimension of the house, our hyperplane will consist of a simple line. Here we can visualize a bunch of points belonging to such dataset. Our goal is to find the line that best explains our data. This traduces in finding the best weights W such that the price is W odd plus W1 times the dimension. For the ith data sample, we call our target variable T sub I, our features X sub I, and the weights that we apply to our features W. Note that X sub I and W are column vectors, while T sub I is just a scalar. Suppose we have n data samples and we consider m features. Then we define the target vector T and a dataset X. And the weights W. Then our prediction, that from now on we'll call Y, for the ith sample will be Y sub I equals to the dot product between W and X sub I. Our prediction vector, which will have dimension n times 1, will be computed as y equals x times w. Note that the ones at the beginning of each row are there just to take into account the bias w aught. But how can we find the optimal weights? We do that by minimizing the so-called mean square error j in function of w, where t minus y is just the difference, or error epsilon, between the target values t and our predictions y. To have a visual understanding on what we're talking about, the various epsilon sub I correspond to the green segments in this image. Our cost function is just the mean squared error j in function of w. Since we would like to minimize this quantity, we derive with respect to w and set the derivative equal to 0. We then isolate the weights w. Now, before tackling the problems relative with such closed form solution, it is useful to introduce the parameter space, i.e. the space representing all the possible solutions W of our problem. In our trivial example, this space corresponds to all the possible points W such that the coordinates of these points belong to R squared. Each of these points traduces in a different predictor, which is a line, in the feature space, as you can see in this animation. Let's now talk about some problems that can arise from the closed form solution. The inverse of x transposed x is computationally expensive when the number of features is high, being the temporal complexity of such inversion big O or m cubed. Note that x transposed x has dimensionality equal to m plus 1 times m plus 1. The matrix X transpose X isn't always invertible, since X transpose X could contain linearly dependent rows, which implies a null determinant. In such case, we'd have infinite solutions for W. In order to show this last drawback, we'll use a toy example. We have to find a valid predictor for a dataset which contains just 3 samples. We solve by means of the closed form solution. In this case, X transpose X is invertible, and if we plot the cost function J in function of W in the parameter space, we can see that J is a convex function with one single minimum and a well-defined bowl shape. This minimum corresponds to the point W, i.e. the blue dot which appears at the base of the bowl, which corresponds to the following predictor line. That last example is the ideal scenario, but it is not always the one you'll be dealing with. In fact, there are some observations to be done regarding the dataset to be used. Now let's compute the closed form solution for another example. Here, our data samples are pretty bad, since there doesn't seem to be any correlation between the independent variable, m², and the dependent variable, the price. We will observe that the inversion of the matrix X transpose X becomes problematic. As you can see here, we cannot invert X transpose X, since its determinant will be 0. By plotting the cost function J in the parameter space, we would obtain a sort of parabolic cylinder, whose minimum has infinite solution that we can find by gradient-based techniques. Part of these solutions correspond to the following predictor lines. Lastly, it is opportune to remember that our dataset needs to have a number of samples greater than the number of parameters to be learned. Being m the number of features of each samples and n the number of samples in our dataset, we need to satisfy the constraint n greater than n plus 1. Let's reason why through a simple example. Suppose that you have been asked to find the model that best explains a dataset made of 2 samples, n equals 2. Suppose that each sample is represented by 2 features, m equals 2, and that we need to predict a value t. In this scenario, we are not satisfying the constraint since 2 is not greater than 2 plus 1. What are the consequences? Of course we will get a perfect fit. There are infinite planes which pass through 2 points. We'll find at least a model that passes through all the data. More specifically, we'd find one solution in the n equals n plus 1 case, an infinite solution in the n less than n plus 1 case. We have found a very bad family of models because they are an exact representation of the training data, which translates into a very obvious overfitting problem. Generally, we want n much greater than m. That was it for today's lecture. For doubts and suggestions, you can comment below. Thanks for your attention.